6.2 confidence intervals for the mean where sigma is unknown. So last time we talked about when sigma was known. Today, sigma is unknown. So what do we have? We got a random sample drawn from a population where either n is greater than or equal to 30 or population is normally distributed. Okay? Then what can we say? We can use the sample standard deviation S. Since we don't know sigma, we can use S, the sample standard deviation, to estimate the population standard deviation sigma. Okay? So when we use the sample standard deviation, the distribution is no longer standard normal or normal, but yet a t distribution. The sampling distribution of x bar is not normal, but rather it's a t distribution. All right, t distribution, otherwise known as the student t distribution, was developed by William Gossett. Who worked at a brewing company. Okay, might have heard of the brewing company. Pretty famous dude. He was kind of a Renaissance man. He developed a student t distribution. Had to call it the student t because he didn't have a PhD. He wasn't one of those big old nerds yet. He was a pretty smart dude and came up with the student t distribution, helping out with sample sizes that were not particularly large. All right, so properties of the t distribution. Number one, the mean is equal to the median, which is equal to the mode. So the mean, mu, is equal to the median, equal to the mode, and that's all equal to 0. 0's in the middle still. Okay, it's bell-shaped. Obviously, you can see from the picture. And symmetric. About the mean. Okay. What else? The total area under the curve. If I'm looking at the area under the curve, that total area is equal to 1. Okay. The tails. The tails are thicker than the standard normal. Okay. Standard normal. The tails are thicker. So if this black curve is the standard normal, then the tails, the student distribution, the t distribution kind of looks like this here, right? Now, you've got different t distributions depending on a change that I'm going to talk about pretty soon, but for now, let's talk about this. The standard deviation varies with the sample size. Okay, So the standard deviation varies with the sample size. So as our sample size increases, we become more and more normal shaped. Okay? So 6, what I kind of hinted to just a second ago, it's a family of curves. Okay? The degrees of freedom, abbreviated DF, okay, degrees of freedom, right? Degrees of freedom is calculated, it's calculated for this particular one, n minus 1. And here's how I want you to think about degrees of freedom, okay? If you have 25 chairs in a classroom, right, the first person walks into the room, they have the choice to sit wherever they want to sit. The second person walks in the room, they have the choice to sit wherever they want to sit except for in the chair that one person's already sitting in, right? You do this all the way until the 24th person walks in the room, and that 24th person only has one chair and then another chair. There's 2 choices to pick from, but they do have the freedom to choose. The one person who doesn't get the choice of where to sit is that last person to walk into the classroom. They're late. They got to pick that first seat right in the front row, right? So they're the one that has no freedom of choice. So the degrees of freedom, everybody gets a choice except for that one last person. So the first 24 get a choice, but that 25th person doesn't. So when n equals 25, 24 of them, n equal to 25 gives you a degrees of freedom of 24. 24 get that free choice. So that's how I want you to think about it. Okay? So as my degrees of freedom increases, so maybe this is a degrees of freedom equal to 10, okay? That green curve. This pink curve, maybe it's a degrees of freedom equal to 20. What's happening here? As my degrees of freedom increases, it becomes more and more closer to the normal, okay? So as the degrees of freedom increases, the t-distribution becomes the standard normal distribution, okay? Standard normal distribution. So if the distribution of the random variable x is approximately normal, then t is equal to x bar minus the mean over s divided by the square root of n follows a t distribution, okay? So critical values are known as TC. So if you're asked to find TC, that's a critical value, okay? So this formula sheet, this little, not a formula sheet, but rather a table, the T table, is in your Blackboard. When you go into your Blackboard, you will see this and you can print it out. I suggest you print it out for your test, okay? That way you'll have it sitting in front of you while you're working through your problems. So it even explains to you what's going on here, how to work this. When the degrees of freedom, when you don't have the degrees of freedom in your table, then you use the closest one less than the value that you need, okay? So it explains it to you right there in your table. So we're going to do an example just to make sure that we understand what's going on here, how to find the critical value, okay? So find the critical value TC for a level of confidence C equal to 0.9 and sample size n equal to 22, okay? So that means we're going to go to this table here, all right? And what are we going to do? We're going to look for C 0.9, okay? So I'm looking here, I see level of confidence 0.9, okay? So I know I'm in this column here, right? And I have a n equal to 22. N equal to 22. So what is that? N equal to 22. That gives me a degrees of freedom equal to n minus 1, which is 22 minus 1, which is 21. So I go to my 21 row, and then I go over, and what is it? It's a critical value of 1.721. Right? That's my critical value right there. Hopefully that makes sense to you, how you find this. Okay, so to do this, you need the C. You need the C and the degrees of freedom to get your TC, your critical value. Okay? What if instead n was equal to 67? Well, df here would be what? The df here would be n minus 1, which is 67 minus 1, which is 66, okay? 66. So I look down here and I see 50, 60, 70. I don't see a 66. So what does it tell me? It says when the degree of freedom you need is not in the table, use the closest degrees of freedom in the table that is less than the value. So I want a DF of 66. I don't have it. What's the closest one less? It's 60. So then I go over here and I look at my number for C equal to 0.9 and DF equal to 66 gives me a DF of 60. So that gives me a TC of 1.671. Okay, so that's how we work it. We just go down. Okay. All right. So here is what I want to do. I want to give you the formula, and you make sure you know how to do this, right? So I want you to know how to find the margin of error for mu. Margin of error for mu, all right? So E here, so this is when sigma is unknown. If sigma is unknown, what's that mean? That means we got to use S, right? So the margin of error, E, is equal to the critical value, TC, multiplied by the sample standard deviation divided by the square root of n. Okay? So what I want to do is I want to find the margin of error given C 0.99, S equal to 4, and N equal to 25. Okay? So when I look at this, I'm just going to plug into my formula right here. Okay? I don't know TC yet, but I know that S is 4 and I know that N is 25. So I go ahead and plug that in. So really all I got to do is figure out TC. So I need 0.99 and I need my degrees of freedom. Well, my degrees of freedom is N minus 1, which is 24. Okay? So I'm going to go up here and I see 24 right here. And 0.99, look, level of confidence. We're only dealing with this top row right here. That's the only thing we have. Okay? So I go down, I go over, and it looks like 2.797. So this is 2.797 times 4 over square root of 25, which is 5. Multiply through, I get 2.2376. So if I rounded 3 decimals, 2.238. And that is my answer. That's the margin of error rounded to 3 decimal places. So you round it to whatever it says. Now the confidence interval for mu unknown, okay? Confidence interval, we've talked about this. What's always in the middle for my confidence interval? It's the point estimator, right? What's in the X bar's in the middle. I go out a minus error one way and a plus the error the other way, okay? So if I was told like that 10 was the lower bound and 14 was the upper bound, what would be in the middle between 10 and 14? It would be, so you might be asked like, what is X bar? Well, X bar for an interval that was like from 10 to 14, right? That would be like 12. It's in the middle, it's the average. And what would the error be equal to? Well, how did I get from 12 to 10? I subtracted 2. How did I get from 12 to 14? I added 2, so the error would be 2 there, right? So hopefully that helps you out thinking conceptually about it. The formula is X bar minus E less than the mean, which is less than X bar plus E, okay? But what is E? E is TC times S over the square root of N. And then I have X bar, and the only thing different is I have a plus TC S over the square root of N. Okay? And this is true if I have a random sample with N greater than or equal to 30, or population is normally distributed. Okay? That's the key there. Population normally distributed. Okay. So here's my problem. I want to assume a population normally distributed. Boom. I got the car keys to the Ferrari. Now I can go driving. Given a random sample of 5 people, the mean driving distance to work was 22.2 miles and the standard deviation was 5.5 miles for the sample. Find the margin of error and construct a 95% confidence interval for the population mean. All right, anytime I see a word problem, I go straight for the numbers. The first number I see is 5. What does 5 represent? 5 represents N. That's how many there are, okay? The next number I see, what's the next number I see? 22.2. That's the mean. It says mean. Mean, I should think X bar, the sample mean, 22.2, okay? All right, next up, I see 5.8. What is 5.8? It says standard deviation. Now, I cannot stress this enough. If it says standard deviation, this is S. The only time it's sigma is when it says population standard deviation. It's got to have the keyword population to be sigma. If there's no population in there, then we assume that it's S, and that's what tells us if we know sigma. If we know sigma, we use Z, and if we don't know sigma, we use S. The T, which is going to say for S, sample standard deviation, 5.8. All right, we want to find the margin of error. So I got to find E, and I need to construct a 95% confidence interval. 95%, this is my C. C is 0.95, okay? So, how do I do this? Find the margin of error. E is equal to TC S over the square root of N. So TC, how do I get TC? I need C, and I need the degrees of freedom. What's my degrees of freedom? It's N minus 1. So N minus 1 is 5 minus 1, which is 4. So I go to my chart. I look up 4 and C95. So I have 4 and 95. So that's right here. So that's 2.776. Okay? 2.776 multiplied by 5.8 over the square root of n, not the square root of n minus 1, but the square root of n, which is 5. Okay, so don't let that trip you up. Multiply this through, and what do you get? What do you get? You get 7.2005, rounded to 3 decimals, that's 7.201. Okay, 7.201. All right. If I look, I need to have a 95% confidence interval. The formula says the mean is between what? X bar minus E and X bar plus E. If you calculate E, then this problem gets really easy, all right? Because X bar is what? It's 22.2, and then I subtract what? Looks like I'm just subtracting 7.201, right? And then I have the mean in the middle, and over here I do 22.2 plus 7.201. So looks like the mean is between, I don't know, 29.401 and let's see, I guess that would be, shoot, what would that be? Would that be 14.999? Yeah, maybe so. All right, if I'm off a little, don't worry too much. It's essentially 15 and 29.4, correct? So what do I say? How do I write this up? With 95% confidence, you can say that the population mean driving distance is between 15.0 and 29.4 miles. Okay? So that will be my final summary of what's going on there. Okay.